You should be able to see my slides, right?
Looks good.
Okay, perfect. So yeah, so I'm going to talk. So I'm Lois, as you said. I'm a machine learning engineer at Zama. So we are a company based in Paris, focusing on fully homomorphic encryption. And the talk of today would be on privacy preserving machine learning using fully homomorphic encryption, which is the tech that we are developing. So first of all, why? Why is it of interest to present this to the Flower community? So as you all know, Flower does mainly federated learning to do private training. So without leaking the data to a central entity. And basically what we try to do is to do the inference in a privacy preserving mode. So you use fully homomorphic encryption to do private inference. Yeah, so that's really a complementary technology to what Flower provides. And so this is why it's interesting. So fully homomorphic encryption. So first, what it is. So I'm going to say FHE for short. It's just the acronym. So let's dive in. This is a typical use case of what happens in the web right now. So you have a client and a server, and so this client sends some data to a server. The server decrypts the data, computes some function or some code over the data itself, and then the result is encrypted and sent back to the user that can then decrypt the result, right? But in this scenario, the server is actually seeing the user's data. So he can collect the data and the user cannot do anything to defend against it. What FHE provides is the ability to do basically the same thing, but with the function evaluation done over the encrypted data. So the server never sees the data itself, making data collection irrelevant. As you can see in this diagram, the basic stuff is the same. So the client encrypts the data, sends it to a server. The only difference here is really that the server isn't going to decrypt the data to process it. And so only the client can know the data and the result of the function itself. So that's really, so the main idea of FHE. At Zama, we focus on a scheme of FHE called TFHE. And basically, we have 3 building blocks. So we are able to do addition over ciphertexts, multiplication with a constant, and table lookups. So these are our 3 atomic building blocks, but thanks to those operations, we can then do much more complex things like, so for example, we can do also multiplication between encrypted data and a lot of complex functions. The more graphical example that we could think of is encrypted image filtering. And so we have a Hugging Face demo actually that does that. So basically you have a client that has some image. The server is capable of doing some processing over it. And so this is what actually happens in the space. The client sends the image encrypted. The server does the computation over the encrypted image, and then the client gets back the image that has been processed. And if you think about it, going from hard-coded kernels to fine-tune and learn kernels isn't that hard. So basically, you could do the bridge with convolutional network pretty easily. And this is what we are focusing on machine learning with FHE. So in fully homomorphic encryption, we have what we call a FHE circuit, which is a set of operations, dot products and univariate function mainly. And this is kind of a representation of a FHE circuit. And if you think about it, it's incredibly similar to a neural network, right? You have those neurons and then those nonlinear function that you're applying. So the basic idea was to convert a machine learning model to a FHE circuit, since the idea is that it's quite similar, similar objects actually. And so we packaged all of this into a Python library called ConcreteML. So everything's open source on GitHub if you want to check it out, and open issues and so on and so forth. And also the best way actually to have a technology that's, let's say, robust is to have it open source so that people can try it out and do some feedbacks and so on. So as I mentioned in the beginning, this is really complementary with federated learning, as we mainly tackle the inference part of the machine learning models, and we actually have some use case example on importing a model trained from federated learning to FHE. So yeah, the main goal of the library really is to bridge the cryptography world with the data science world. And so we try to provide an API that's as close as possible to what data scientists are used to. And so that they don't have the need to know anything about cryptography or FHE in particular to use the library. So the APIs that we use are very similar to what scikit-learn provides. And we also have some endpoints for Torch, TensorFlow, ONNX, and other machine learning frameworks. So really trying to be as close as possible as from the data science toolkit. We have support for a large variety of models. We split them into 3 categories, mostly. So tree-based models, linear models, and neural networks. As you can see, we have support for most typical models. If you want to improve that list, you can go on and contribute on GitHub. We are very open to contributions. And if you see that we are lacking some models, please ping us and we'll be very happy to add some support. Something that I didn't mention or that you might have seen in the first slide is that we can only do computation with integers. So this is kind of the main bottleneck that we have. But luckily for us, there is a whole field of quantization that's been really important in machine learning and most importantly in deep learning. So this is a whole field that's been developed mostly for embedded systems and large models that have some memory bottlenecks. But we benefit a lot from it since there is this whole toolkit of quantization that's already existing and that we can just use to compile to FHE. So this is really a good point for us. So the first family of models that I mentioned are tree-based models. So we have support for XGBoost classifiers. So that's great that Flower is actually improving on that. And as you can see, the API is actually quite similar to what you would expect from scikit-learn or XGBoost. You just have some model instantiation, you do a fit, and then you can predict your model on the test data to evaluate the performance. And so there are a few differences with what you would expect in scikit-learn. We have a supplementary argument called nbits that's going to define the number of bits over which we are quantizing the data for the model itself. So basically the whole quantization stuff is happening under the hood and the user doesn't have to care at all about it. So everything is handled in the library. And then we have a compile function that actually does the compilation to FHE. So this is the conversion between a floating point quantized model, let's say. I mean, clear world, but quantized model to a fully homomorphic model. And so we have a few functions to test that the fully homomorphic circuit actually works as expected. We have a simulation mode that allows you to iterate fast on the data and check that everything is happening correctly. And we have an execution mode that really does the computation in FHE so that you can actually evaluate the time that is going to require to do the inference in FHE. And why I am saying that is that actually doing the computation in FHE takes a bit more time than in the clear. So you have a trade-off between the number of bits that you are actually using for the quantization and the speed of the model. Because the table lookup operation that I explained earlier is actually one of the most computationally intensive computation. And so it's really kind of the bottleneck. And if you can reduce the bit width of this table lookup, then you are accelerating your computation. So what you can see here is a XGBoost classifier trained on the spam-based dataset for different quantization bit widths. And so you can see that for a number of bits equal to 8, we have actually the same exact performance as the floating point model. but we have an inference that's going to take a few seconds, like 13 seconds per sample, which is a lot. But if we reduce the number of bits to 5, for example, we are below 1 second per sample, but we have basically the same accuracy as the floating point model. So there is obviously this trade-off that the data scientist has to fine-tune, but we make it super easy for the user to actually generate those curves, and so they can fine-tune the accuracy trade-off with the timing of inference. The second type of model that we have are linear models. So here, logistical regression. So for linear models, since we are not doing any univariate function or table lookup, this is going quite fast, and we can go to higher bit width without any trade-off in speed. So that's actually great. So we have great support for linear models because of that. The API is basically the same as before. The n-bit arguments, the compile method, and then the FHE argument. So what we can see here is the comparison on two data sets of a floating point model in the middle and the concrete ML model, so quantized on the right. And so basically the only difference that we can see is on the borders. So here we have a high bit width. So basically let's say the separation curve here is basically the same between the quantized and the floating point model. But the difference is outside of the data sets, you don't have any guarantee that the quantization is going to behave correctly. So this is kind of a showcase of why it's super important to have a representative data set when you are training and compiling with concrete ML, with respect to maybe other libraries where you can maybe extrapolate a bit more. Here it's very important to have the correct distribution in the data that you are providing. And last but not least, we have support for deep learning models. So we have support for both built-in models, so multi-layer perceptron with the same scikit-learn API. So this is what you can see here. So we have the same kind of behavior as before on the curve. Here we see that we have a lower bit width, so we can see that the separation is a bit more, let's say, squared. But basically, we can see that the overall accuracy isn't changing that much. In the case of the middle, yeah, but in the other data sets, you don't have much differences between a float model and a quantized model. So this is great, actually. And we have a white paper for that and for the tree inference, if you want to take a look at the internals of how and why that works. And yeah, last but not least, we have a support for custom neural networks. So you can provide any torch model or TensorFlow model that you have, and you train it, for example, as you would with a flower or on your own data. And then the quantization is going to be either because you train the model with quantization over training, or because we use post-training quantization. So basically, whatever your model is, you should be able to provide it to the compiled torch model or compiled Brevitas cat model, and everything is going to be working flawlessly. And yeah, so the same object is going to be returned, and you are going to be able to do the inference in FHE without any issues. Because this is obviously a flower meetup, we have the use case of training a model with flower and then importing it in concrete ML. So if you train your model actually with the torch, you don't have any work to do. It's just taking the torch weights and then compiling it to FHE. If you have a scikit-learn model, then you would have to call the from scikit-learn model method, because we still have to do some conversion to convert the floating point model to FHE. This is only supported for a limited number of models at the moment, but we are trying to expand it to tree-based models, for example, and so on. So this is something that we are going to expand on in the future, for sure. So as I explained, the process of developing a deep learning model for FHE is kind of the same as a typical machine learning workflow, with just one more step, let's say that, or two more steps that we are adding. So the training is basically the same. So you train your model with the tech that you want, whether it's quantization or training, federated learning, or whatever you want. Then you have to do a cycle between fine-tuning some parameters and evaluating it in simulation to assess that the accuracy of your final model will be correct in FHE. So you have multiple arguments that you can play with. As I mentioned, you have the number of bits, but you can also, for example, play around with the pruning of your model if you want to accelerate it a bit or reduce the bit width and stuff like that. And obviously you have, after each choice of hyperparameters, you have to do the simulation to evaluate the fact that the inference in FHE is going to be correct and you will have the accuracy that you would expect. Since we think the examples is the best way to make ourselves clear, let's say, so that user can just copy paste snippets of code or adapt to their use cases. We have different kind of use cases in the library and on Hugging Face. So we have examples on the MNIST, Cypher10, image filtering, as I mentioned, federated learning, obviously, and also some stuff like sentiment analysis, where you do some kind of computation in the clear to extract some features, and then you do the model inference in FHE. Yeah, and performance-wise, we are actually pretty similar with floating point models now, at least on quantization aware training models. So on Cypher10, for example, we reach 90% top one accuracy, if I remember correctly. And we have 2 minutes per sample inference time, but we are improving a lot of that. Like each quarter, we are improving the runtime by a lot. So who knows in 6 months, what's the runtime going to be? Thank you, I guess, thank you for the invitation, Nick. And if you have any question in the chat, it's the moment. Or if you have, you are a bit shy, you can ask on our Discord server or our forum. And if you have any issue, you can just ping us on GitHub. Thanks a lot.
Thank you. That was wonderful. It was really interesting to see how these two things, like Flower and Zama, can work together, and also there's just the work that you're doing in isolation over in Zama and how those could be used by themselves as well. It's really interesting. I think if there's anyone in the audience that wants to ask a question, you could raise your hand. We don't always do it this way, but I think that's a reasonable approach. I will allow you to talk, and you can just put your question over through audio. So the first question has come from Omar. You can now speak, Omar, I think.
Do you hear me?
Yeah, we can hear you.
Yeah, thank you for the excellent presentation. Also, congratulations for the good work in Zama. I have question of as far as I know that homomorphic encryption works only on linear functions. Is the library that use Zama used in Zama take of care like for the logistic regression take of the sigmoid function in the server side or in the client side?
So I think Omar's main question was about linear models, and will it work with linear models of different kinds? I think that's my interpretation. What would you say to that?
So yeah, so actually for linear models, you have basically two choices. Either you do only the linear part in FHE, in which case it's going to be super fast and you can go to crazy bitwidth and everything is going to be working nicely. Or you can do let's say the activation function or the non-linearity in FHE, and then it's going to be a bit slower. But usually, yeah, I mean, both would work, but we would recommend doing the nonlinear function in the clear and then just doing the computation to preserve the weights in FHE.
Okay. Sounds good. And Omar, if you have follow-up questions, feel free to like post them in Zama or in Flower, or we'll find a way to close the circle on this if you have other questions. Any other questions? And feel free to raise your hand. Otherwise, I can look at some of the Slack ones. While we wait, I'll have a look in the Slack. One question is, what's been the most popular use case so far that you've seen people use this for, given that there's a few, I guess there's a few limitations, is what people are saying. So what do people tend to be using them for right now?
So actually, we have a lot more questions that we were, let's say, expecting on like deep learning models. And so actually, we have some people doing deep learning in FHE and in decent timings with since we have a lot of parameters that we can play with to speed up the models, as long as the depth of your model isn't too like big, you can still do some things and interesting things actually in FHE. So for example, the VGG11, we run fully in FHE and everything is going to be fine.
Did you say VGG11?
VGG11, yeah.
Yeah, I
fully
see.
in FHE. But you could also kind of mix and match. So you can have like some part of the model that's non-critical being done in the clear, and then the rest of the computation be done in FHE. So for example, if you think about large language models, you could do, I don't know, some part of the public model in the clear, and then the fine-tuned heads in FHE, and you wouldn't have paid the cost of the whole like FHE computation. You would only pay it on a small part of the model. But I guess for now, most of our use cases are on tabular data. Yeah, we have a health prediction. I mean, in health, we have a lot of use cases that are quite interesting because it's a kind of the field in which the data is more sensitive.
Makes sense. I guess a question I have would be, what are the ways that you think FHE and FL could be used more, I don't know, deeply in the future? Like, I guess you've got an example that's quite powerful by itself, but I suppose there's many ways that these two things could be used together to build a system. So what are a couple of your favorite ones?
My favorite one actually is the one I worked at previously. So in my previous company, we did breast cancer detection based on radiography. And actually, one of the main bottlenecks was getting the data from the centers themselves. So actually, you could do federated learning with the data from each mammography center, let's say. And then once you do the production phase, let's say, then you would do the computation in FHE so that the central, let's say, you have a central serving server and you are serving all of the radiology centers through that, and the computation being done in FHE to preserve the patient's data, for example.
Oh, I see. Yeah, I see.
Because actually, the radiology center don't often have the compute power to compute those models. So this would be a way to centralize the model itself, but without seeing the data at inference time.
And there must be also a use case related to, you could federate the learning of a model once you have that model and you really care about protecting those weights, maybe because there's a really interesting IP there. Then
Yeah, exactly.
all the inference could be done in this sort of style if you're really conscious of that.
Yeah, exactly.
Yeah. I guess it also would lock down any other types of inference that you didn't want to be possible because the weights are known. So only the API you can expose will be the one that you could run. You can't do something else with the model.
Yeah, exactly. Yeah, for IP protection, that's another use case. Yeah, for sure.
Cool. Well, I'd love to be able to see a few of those examples come to life, and I'm sure maybe we could work together in the future to see some of them realized. Excellent.
Yeah, pleasure. We are very happy when people try to build stuff with our tech.
Yeah, definitely. So likewise, yeah, we love to involve a bigger sort of community building on these things. Okay, well, thank you so much for today. I really appreciate your time and sharing with us. Yeah, thank you.